Hello, everyone.
Hi, Dr. T.
Hello. Cool. Hey, let me get my headset here. Get my headset in. Headset. And get set. Go. See what I did there? Oh my gosh. So clever. Oh my gosh. Calvin is here, uncharacteristically not pictured. Pauline is here with her picture taken in front of
It's in front of UOP. That's my graduation gown.
Oh, got it. It says university. Right. Got it. Excelente. All right, so I'm going to make this a little bit smaller. Oh, not that small. There we go. Oh yeah, I gotta get the promised protein folding quiz document here. Okay, this is gonna go. Okay, so it's 5:59. That means it is less than 1 minute to me saying something possibly relevant. Adam, how are you? I must say, Adam.
Yes.
I am super proud because I can see you.
Uh-huh.
And I'm super double proud that I can see Calvin. Yay!
I'm double proud that I'm eating pizza.
Oh, with a fork.
It has ghost chili, so I don't want to touch it.
Oh my effing beep. Yet you will eat it.
Mm-hmm.
You won't even touch it with your fingers, but you will put it into your mouth.
Yep.
Knowing full well that it's going to make its way all the way through your GI tract.
I've never had digestive issues with spicy food.
Well, can count yourself lucky then, sir.
Every day I do.
Oh my God, that's amazing. My son likes spicy food too. I cannot abide it.
Mm. How spicy does he like it?
Oh, he got a little surprised once, but he's always like, no, maximum, you know?
Mm. I got something for him.
Oh no. No. You guys all just want to kill me, huh? Y'all want to kill me.
Did you see it?
No, I didn't catch it. What was it? Oh, ghost chili. Smoked ghost chili. Oh my gosh. Are they whole, pickled? What are they?
They're crushed. It's like a little pepper grinder.
Yeah, like oh my gosh. Ah,
It's from Trader Joe's. I put it on everything.
oh my bleeping gosh.
It's amazing. Not ice.
Dan, you're here. Hooray!
Hey, what's up?
And Carla, our biophysicist, is here. Yahoo! And Aditya is here, our all-around genius. Yay. Okay, so let us continue. Oh, so we got through the basically the introduction last time, right? And let's start on the experimental, and we're going to make a timing diagram. Okay, so I'm probably going to use my stupid ass document camera for that. Did I say that on camera? I will deny it, and then you'll have to get the evidence to smash me. Okay. So, hey, Carla, do you think you ever might want to work for Martin Grubely?
I don't know. I mostly like misfolded proteins and intrinsically disordered proteins. I haven't heard of his name in the field, so
You personally like them?
well,
My gosh.
that's my interest in the field.
Oh, come now. We can't be that narrow. You're not like 100 years old, are you?
Well, I mean, I'm not, I'm open to other things, but that's just my general, like, when I go to, protein folding stuff, it's usually about misfolded proteins.
Misfolded. Like, is this because of Alzheimer's?
No, I just think prions are really cool.
Prions are weird.
I think they're really
They're-
cool and terrifying.
They are weird and terrifying and cool. So when you guys see this, do you see all of everybody's faces or just my ugly mug?
It depends on how you click your settings.
Okay, so well, right now, do you see everybody or just me?
I see like 5 people.
Oh, okay, cool. Excellent.
We can change it to only see you or the speaker.
No.
whoever's speaking.
I was just hoping that, because like when I do the recordings, it only shows me.
It's whatever your settings at for the recordings.
I don't freaking know.
Well, when you post the recordings on YouTube, usually it will highlight the face of like whoever's talking.
Mhm. Right.
But I think there are settings where you can record it and have other people show up.
All right. Too damn complicated. Richard, hello. I am super enthused that you're here. And you appear not to be at work. Did you get laid off?
Not yet.
Oh, good. Excellent. All right.
I hope
So-
you don't. That's
Right. I hope you don't too. I mean, I'm not saying that I'm just like, I'm not going to, it just came up, whatever. So now, I'm not being backed into a corner here. So let me get on with things here just a little bit. And I want to draw you a timing diagram of this experiment. Timing diagram. So put this guy bunk up here. I'm going to tell it to focus. Maybe even focus on my hand. There we go. Oh, my hand sure looks weird, doesn't it? It's like a creepy hand. It's an old man hand now. You know, it's weird because as you get older, you know how everybody gets angrier as they get older? Just angry. I'm angry all the time now. Because you don't fucking feel any different. It's your fucking body's all breaking down all the time, and like your back hurts and your feet hurts, and your face is all wrinkly and ugly, and your skin's hanging off your body, and it's horrible.
Are you stretching and exercising?
Shut up.
Just saying.
Yeah, it looks like I'm stretching my skin is what it looks like. I've exercised my whole goddamn life, you know. And then about 3 years ago, I had a heart attack.
So?
Well, shut up. That's not so. You've never had a heart attack, Mister
No.
Eating pizza with a fork.
Homemade pizza. So it's
Oh,
yeah.
pretty good. I want some.
So it's
Pecan. It's healthy
Yeah.
pizza.
It has
healthy
ghost
pizza.
cheese. It has
I know it has ghost peppers.
No, it has goat cheese.
Oh, goat cheese.
Oh, you
sorry.
fancy, huh?
Yeah.
Oh my. Oh my.
Anyway, you're supposed to increase your stretching and exercising as you age, not decrease.
Adam, are you eating pizza from Dr. Grazioli's recipe?
No. That's not pizza to me. That was just bread.
Oh, gee. Oh, my
Don't
God.
tell Dr. G. I won't tell him.
I was going to post a picture of mine, but this is slightly different than what we normally do. Anyway.
Kenya, it is so good to see you.
Thank you. See, I'm not being healthy. I'm eating Chex Mix.
You're going to live to be 250.
I better. My grandma lived to be 99. Shoot.
I rest my case. Hikun, it is awesome to see you too. Yay.
See you too.
Excelente. I am not saying that to Pauline, Ivy, Kai, or Lily for reasons which should be obvious. But the rest of you, thank you. So, timing diagrams. Timing diagrams. So, in a timing diagram, we have something versus time, right? And the first thing to know is that we have a synchronously repeating laser. It's actually a YAG laser, which is Q switched. And the Q switch is a Pockle cell or an electro-optic modulator, which switches polarizations periodically, right? And the idea is that it switches to an unfavorable polarization, which allows a population inversion to build up. And then it switches to a favorable polarization, and then the cavity dumps, and a pulse of laser light is emitted. So the amplitude of the pulse is not always perfectly well defined, but they're very regular because they pulse every time you Q switch the electro-optic modulator. So it's in the cavity, right? It's effectively in the cavity. It's between the two mirrors, right? And every microsecond or every in this case, oh my God, I forgot the stupid rep rate. In this case, every 15 nanoseconds, holy crap, every 15 nanoseconds? That is one hell of a high rep rate. Well, let's highlight that, mother. Every 15 nanoseconds. Come on now. Stupid PDF. Every 15 nanoseconds. So basically what that means is that they have this ultraviolet pulse that is pulsing every 15 nanoseconds. How do they make an ultraviolet pulse, you may ask? Well, they frequency triple a YAG, which is, come on, where's the YAG? Where is it? Where is it? Oh, this is actually not a bad place. No, oh, they don't have it. It's in one of the other papers. Anyway, they frequency triple a YAG. And so that means that 1064 divided by 3 is 354. Whoops. That's not right. Huh. 280. What's 280 times 3? 840. Maybe I don't know if this is going to help, but let's see here. 10 to the 7th over 1064 is 9398. Three times that is 28,195. And then that's 354. Okay. So they have some other Q switch laser to create a to create an excitation every 15 nanoseconds. Could it be that 280 is the fourth harmonic? Oh yeah, 266. Anyway. They could use 2 stages and they double it twice. Yeah, they probably double it twice. And the actual excitation is 266 nanometers. Okay, sorry. I've been jotting on my stupid paper here and you guys haven't seen any of it. But 1064 nanometers over 3 is 354 nanometers. But that's not how they do it. I thought for sure they said they tripled it. But it looks like what they do is that they double it twice. So in that case, they've got 1064 divided by 2 is 532. And then 532 over 2 is equal to 266. This is twice double. And that makes sense because a YAG is a very reliable high rep rate laser. You excite it continuously with flash lamps, and then it Q switches and I don't know, whatever. I think it's a YAG. But in any case, what happens is that it creates a train of pulses like this. So this is the excitation laser, right? And then the emission PMT, what it's doing then is it's going getting excited every 15 nanoseconds. Like that, right? So, and what they're trying to do is to establish the folding state based on the analysis of this transient here, right? So each of these will create a point that goes between native and molten globule. And so they'll analyze this guy, and it'll be like molten globule, and then they'll do something else, right? And then it'll be like native, more native, more native, more native, right? And then this will go on, and then they'll repeat this cycle. So let me see if I can redo this then. So what we're going to have is the excitation pulses. And I'll make them very short, maybe less than a nanosecond long. Right? But happening regularly. And we'll have the transients come out of those. Like that, right? EX, EM, and then the percent native, right? Between 0 and 1 will be derived from the dynamics of this decay, and the shape of that of the decay curve there. So this guy might be, it might start out cold denatured, right? And it'll just be reading 0, 0, 0, 0, right? But then what they do is that at some point, they have a heating pulse. This heating pulse is off, and then it's on for it's 15 billion Kelvin per second, right? Isn't that right? No, 5 billion Kelvin per second. 5 billion Kelvin per second. And they go about, let's see here. They go about 20 Kelvin, right? And so this is 4 nanoseconds long, actually. So this is actually shorter than one of these pulses, right? And then, so this means that this guy here will be heating. And afterwards, they're going to look at the change between molten globule and native. Right? So this is, say, still molten globule here.
Dr. Terrell,
Yes.
we're still looking at
Oh, sorry. So then what'll happen is that here's the this is the 5 nanosecond heating pulse, and these are every 15 nanoseconds. So it's not perfectly to scale here, but this is actually shorter than the transient between these. And then what they'll do is they'll look at then over time this guy is going to start, the analysis of this curve is going to start to change, right? So this is going to do something like that, right? So now let me ask you something diagnostic here, which is, how could I plot the temperature versus time along a common axis? And let's do the shame game. Okay. So what I would like to do is plot temperature versus time along this axis. So what is the lowest temperature that this system can or will assume?
Was it -4C?
Exactamundo. So before, this is the heating pulse, right? So what's the temperature going to be before the heating pulse?
Should be -4.
-4, exactly. -4 degrees C. Now, how hot does it get after the pulse? Well, it's 5 billion Kelvin per second for 5 nanoseconds, 5 billion Kelvin per second, or 5 Kelvin per nanosecond, right? 5 Kelvin per nanosecond times 5 nanoseconds equals, how hot is it going to be after the heating pulse?
So 21C.
21C. All right. That's 2 for Richard. Okay, that's 21C. So now where along this time axis will it be 21C? So I'm going to keep putting records here, and you tell me where it's going to get to 21C.
There.
Ah, Kenya, you're
It's
absolutely
gonna be
correct.
like, yeah, by the 5 nanosecond thingy.
Right, it'll be at the end of the 5 nanosecond pulse. Excelente. All right, so now what happens leading up to that point?
It should be increasing.
Yes, linearly or exponentially or what?
Exponentially.
Nice try. Linear.
Linear.
That's fine. That's fine. That's a linear increase. And the way I wrote it was that the power input goes from 0 to a maximum and from maximum back to 0. That'll make a linear increase, but you know, whatever. That's totally fine. So good. Excellent. So now, what is the temperature after this point? Is it falling off like this?
It's linear, so it's gonna be -4.
So this is -4. So what temperature is this?
21.
21. Exactly. Right. So now, moving forward in time, what's happening to the temperature? Does it come right back down? Does it go forward? Does it go down slowly? What happens? Dan?
Exponential decrease, I think.
exponential decay, right? So let me put a few examples out here that might work. We've got that. We've got that. We've got that. And we've got that. This is A, B, C, and D. So, Dan, which of those four is it?
Yeah, well, maybe it's a combination. I'm not sure. The slow, like the ramp from, I don't know, 2 graphs up shows that the protein is slowly absorbing the heat. So I want to say something that's more on that time scale, like on the longer, but also the protein could absorb energy and then, so yeah, I don't know, B or C maybe.
Okay, alrighty. Anybody else have any input there?
Well, didn't you say that because the nanosecond you set it so that it goes all the way up, like from 0 to the
Mhm.
full thing on the, is that delta H? That's why the temperature went from -4 to 21. Like, then shouldn't it be A? Since you're dropping it from the top to the bottom completely after the 5 nanoseconds.
Reasonable. Who else has input? Oh, Aditya, sorry.
Full disclosure, I didn't read the paper yet, but
What?
didn't we talk about the protein like
I'm just kidding.
suddenly taken to the equilibrium temperature at 21 and then like allowed to fold at that temperature? So would it be D?
Would it be D?
I
I
don't
don't know. I don't know. I don't know. You guys have to decide. Carla?
Someone just flatlined.
I think that's Kai.
I'm
Kai,
gonna
are
be
you-
honest, I kind of spaced out and I don't know what we're talking about.
Are you dead, Kai? Are you dead?
Oh, sorry. I just got home. I was in traffic.
Oh my gosh. All right. We just heard a flatline sound, so I thought you might have died.
Oh, I think that was my phone turning off Zoom.
Oh, okay. Got it. I got it. That works. Awesome. Nice to see you, Kai.
Hello.
Hello. So, Aditya is saying it might be more like D. Kenya's going for A. Are there any B and Dan seems to think it's B or C. So that leaves us with absolutely zero conclusion. Carla, do you have an opinion?
Can you ask the question again and explain what the graph is?
Come on. Sheesh. So this is temperature. This is time. This is a heating pulse so intense that the temperature ramps up from -4 to 21 degrees C in 5 nanoseconds, right? Now, what I'm asking is how quickly does it cool off? I mean, who has a cup of coffee nearby? Does anybody have coffee? Does anybody ever drink hot liquids? Hikun, do you ever drink hot tea?
Sometimes.
All right. So how long does it take your teacup to go from, say, 40 degrees to 20 degrees?
Like half an hour to an hour between
Excellent. Great. So let's say that it's, let's say 3,600 seconds. It would be an hour. So maybe 1,800. Let's say it's 1,000 seconds. Let's just pick a round number. 1,000 seconds on this time scale. This is 15 nanoseconds. How long would 1,000 seconds be?
Very long.
Excellent answer, Pauline. If I were to draw 1,000 seconds, if I were to start to go here and say, okay, now we heat it up. Now, over 1,000 seconds, it cools down. Which of these four curves would it resemble?
D.
Sorry, could you say that again?
D.
D is in dog?
Yes.
D is in your puppy?
Yes, my puppy.
Your puppy dog? All right. I think that's the craziest thing I've ever heard in my whole life. But it's absolutely correct. 1 point for Pauline. No points for Dan, because although he courageously answered, he got the wrong answer. Sorry, Dan. I'm just mean as shit today. It's because I'm old and I'm angry. I already explained that. I'm gonna stretch. Yeah, I exercise, man. I just haven't been exercising lately. Okay, so how is it possible, Kai, that after this heating pulse, the temperature is completely static?
Reached max temperature?
No?
No.
The maximum temperature, there is no maximum temperature. We could be vaporizing into a quark gluon plasma here, you know, with a 15 petawatt laser pulse. But we're not doing that. We're just heating it to 21 degrees C, right? And then I am saying that the temperature is completely steady there. And I'm asking Calvin, why? Why is the temperature completely steady for the next, how long before the next heating pulse here? I don't know.
Probably it's in a controlled environment.
Okay. Actually, if you must know, the stupid thing is being actively cooled. It's on this thermoelectric cooler here. This may be familiar to Adam, right? As a thermoelectric cooler, very similar to the ones that they put on computer chips, right? Which, when you pass a current through it, gets a hot side and a cold side. Right? So this whole thing is just being actively cooled the whole damn time. It's being cooled so much that this whole block is minus 4 degrees C. The thermocouple is right here. So technically just that point is minus 4, but hey, give them cut them a break here, right? So why then are we saying that the temperature is steady up here? One last chance to get this one right.
I thought you already talked about it in terms of it's a time scale. It'll slowly come down, but
yeah, it's a time scale. Exactly. And what would you say about this time scale relative to the normal cooling rate of something like this?
well, it's on orders of magnitude different, like you said. So it normally cools down. It takes, hundreds or thousands of seconds depending on the system and the insulation and et cetera.
Right. Even if it took 1 second,
We're on
It would-
nano.
Yeah, this is a nanosecond. So it'd be a billion of these guys, right? So that's why it's effectively flat up here, right? So now this is the brilliance of cold denaturation, right? This is why by choosing a completely artificial system, Grubly was able to make a very fast kinetic measurement because, and complete this sentence for me, it's easy to blank something quickly,
Heat.
but it's impossible to blank something as fast. This word here, Adam got it, was
Heat.
heat, and this guy here is
Cool.
all right. Now that was Pauline and who else? Pauline and Ivy. Excellent. On the board. Pauline for 2. And Ivy for 1. And I think I'm gonna leave Adam with 2. I'm not sure because I don't want to double count. Okay. It's easy. What, Lily?
You gave me 2 and not Pauline,
Yeah, you gave Adam 2 and not Pauline.
but I'm okay with this.
Oh, really?
I'm not okay with this.
Oh my gosh. So Pauline gets 2 and Adam gets 1. Is that how it works? I'm just taking your word for it now because I don't know what the hell's going on. Okay. This is the blame game. No. Blame game.
I thought it
Okay.
was a shame game.
That was yesterday. That was Tuesday. Today it's the blame game. I figure we got to alternate between negative descriptions. So basically, because we use a cold denatured system, we're able to heat this guy super, super quickly, right? And then it just stays hot, right? So now why is the protein not denatured here and then refolded here?
Wait, what?
Okay.
You can't see
Why?
the protein.
Okay, sorry. Can you see my mousy cursory thing?
Yeah.
Okay. My mousy cursory says at this temperature, the protein is cold denatured. It's denatured. Then we heat it at 5 billion Kelvin per second to 21 degrees C, and it is still denatured. Why?
Because it doesn't fold that fast.
Who said that? That was Carla.
Me.
Carla's on the board. Carla, 1 point. Now, what descriptor do we use for that time frame in chemistry? What is the description of the time that it takes this protein to fold?
Kinetics.
Kinetics. Richard, 3 points. Takes the lead. Excellent. So the kinetics are now what we're measuring. And how do we measure the kinetics?
CD spectra?
Oh, was that Carla?
Yep.
Nice try, Carla. But you're wrong. CD spectra is how we get the steady state structural information. But you cannot take a CD spectrum in a nanosecond or in 15 nanoseconds, as the case may be here. how do we measure the protein folding state as a function of time? Lily, you're still not on the board.
Doesn't the paper? Oh,
Oh,
No,
no.
let Lily talk.
Oh. So, is it the fluorescence?
Yes, exactly. We measure the fluorescence decay. Should I give her Lily a point there? I'll give her a friggin'.
Yeah.
Okay, and give Lily a point. Now, Dan, what about the fluorescence decay? I got to give Dan a chance to get on the board here, since he's been holding back.
I would say like the slope of the fluorescence decay.
Exactly.
Like how, yeah, okay.
Exactly, exactly. Now, it's actually a subtle thing, right? So now, before I go into that though, let's ask one more question related to the timing diagram, right? So, how long will it take the folding to happen roughly, according to our read of this paper?
20 microseconds.
20 microseconds, Lily. Boom. Okay, so this is, let's find 20 nanoseconds on this paper. 20 nanoseconds is roughly this long. 20 microseconds is how many of those time intervals? Nanosecond is 10 to the minus 9.
It's 1,000.
Second. Microsecond is 10 to the minus 6 seconds. Adam gets another point. I love it. Great. So it actually takes like 1,000, well, it takes like 1,000 pulses, right? 1,000 of these pulses before the structure has caught up with the temperature. Does that make sense? Ikun, what did I just say? Oh my God, Ikun's not on the board yet.
Oh, I just lost you. Can you
Oh
repeat
my
it?
God. Okay. Ikun, how many, oh wait, what did I say? God damn it. I'm angry again. Something about how long
How many pulses does it take for it to catch up?
Yes, exactly. How many of these pulses, let's say there are 20 nanoseconds, before we have gone, before the protein has completely folded, right? It's molten, then it's folded. Molten, wait, actually that would be here. This is molten, this is folded, right? So this doesn't happen this fast. It actually happens much slower. And how many of these pulses roughly? So let me start you out here. It's about 20 nanoseconds per pulse. And then 1 microsecond for every 1,000 nanoseconds. That's not right. I need something to turn nanoseconds into, no, I need to go with pulses, right? Oh shit, I don't know how to do this. I'm just brain dead. So I'll answer my own question then. if this is 20 nanoseconds and it takes 20 microseconds, then there's 1,000 of these pulses in that transformation, right? So there's about 1,000 pulses per transformation
Wait,
between, yeah.
they're pulsing that entire time?
Yeah. Yeah.
But
Absolutely.
won't the heat increase exponentially to a point past their?
Excellent point. But they're not pulsing with the heating laser.
Oh, this is the infrared.
They're pulsing
thing?
with the, yeah, this is an infrared laser.
Okay, never mind.
And this is a UV laser. And the UV laser is carefully tuned. It doesn't interact with the water, right? If the UV laser were interacting with the water, then this game would be over before it started, right?
Sorry.
No. It's a good point, right? If the UV laser, I just thought of another question for y'all. If the UV laser were absorbed by the water, it would just heat the water and it wouldn't even excite the protein, right? So they have to find an excitation wavelength that's to which water and the buffers and the rest of the protein are transparent. But the tryptophan is not. The tryptophan's a good absorber. Okay. What did I just say, Hikun?
Yeah, I'm still confused about this.
Okay. So how can we bring Hikun up to speed? Dan.
I was gonna say a joke, but
say a joke for God's sake, please. I'd love to hear a joke.
I don't know, something that's fast, bring you up to speed. No.
I love it.
Well, I think maybe what was confusing me, and you just clarified, the UV laser is pulsing. The UV laser is what's detecting the fluorescence, like that initially, or that excites the fluorescence, and then there's also an IR pulse that's heating it up. So maybe there's two different.
Right.
Does that help?
Right. So Hikun. Which laser is used to analyze the structure, and which laser is used to heat the specimen? There's the UV laser, there's the IR laser.
Isn't UV used to heat the structure?
No.
No.
UV is used to analyze the structure. The UV laser excites the tryptophan fluorescence. Then the tryptophan fluorescence decays. And it's the decay time that is then transformed into the percent molten globule or the percent native state protein. Right? And then what they just continually bombard it with these excitation pulses. And that continually excites fluorescence. And then at a certain point, they wham it with this infrared laser. The infrared laser is absorbed strongly by the water. Then in that 5 nanoseconds, the water heats from -4 to 21 degrees C. Conditions favoring an unfolded state to conditions favoring a folded state. And then during this new interval, at which point in time the temperature and the protein are no longer at equilibrium, the protein begins to fold and slowly reaches equilibrium with the new temperature.
By new temperature, do you mean 21 Celsius degrees or?
Right, exactly. 21 C is here, -4 is here, and then this is like almost an instantaneous change, right? And the temperature is roughly constant on this 20 microsecond time scale. And during this 20 microseconds, during which time we continually we're monitoring every 20 nanoseconds, we take 1,000 structurally sensitive fluorescence decays during that 20 microseconds. And as a function of time, then over that 20 microseconds, we map out the folding of the protein. So
I have a question. I have a question.
Yes. Yes, absolutely.
What does it mean when they say in the second page under the kinetics probing paragraph, all infrared and UV probe beams are electromagnetically shuttered during the experiment to avoid optical sample denaturing?
Yeah. So
Denaturation.
I don't know exactly, but so what they mean is that like the IR pulse, it's obviously a pulse, right?
Right.
And so it's off majority of the time, then it's on briefly, then it's off for a long time, right? And then the UV pulse is on and off and on and off and on and off, right?
Mm-hmm.
But then whenever it's not being used, let's say that there's 1,000 UV pulses for a folding measurement, right? That means they'll pulse the IR beam once, they'll pulse the UV beam 1,000 times, then they'll turn it off, right? And then maybe they'll let maybe they'll cool the system back down, let it cool back down to -4, measure the ellipticity, then run the transient series again. So when they say that they're electromagnetically shuttered, it means that they have polarization dependent shutters. They're called Pockle cells or electro-optic modulators. They're just electrically driven polarizers. They don't physically move, but they'll change their polarization state
So
depending on
they divert the beam using.
Right. Yeah, they'll absorb it or divert it or do something like that to it. Yeah.
Got it. Thanks.
Got it. Excellent. Yes. Good question. Okay. So Hikun, somebody think of a question for Hikun to help him understand this process a little bit better. Or maybe Hikun can make a statement or ask a question. Nobody's got help for Hikun here? I know I'm asking you to do my job, but I don't have any ideas right now.
Oh, I got it. I just.
You got it? Okay. Okay, so ask him a question, Dan. Because I don't believe him. I don't think he's got it. I think he's kind of got it, but he doesn't got it.
Can you scroll through the paper real quick? Remind me of the different.
Yeah, absolutely.
Because all I can think of is like the most complicated question that I'm actually wondering about the paper itself. So.
Okay, ask me that question then.
Yeah, it has to do with were they tryptophan residues? Or were they tryptophan? Yes, and they were quenched with some other residue.
Serine, yeah.
Yeah, what's to say? Yeah, the serine. Thanks. What's to say that that actually is a entirely accurate measurement of whether it's denatured or not, because I mean you can have the entire protein folded and you know they'll be very near each other, or you could maybe have the entire protein messed up and separated, yet they're accidentally near each other. I don't see how it's a guarantee that they're I don't know, bound or something like that.
Excellent question. And there is no guarantee at all, period. Right? But I want you to pay attention as we go through this paper, and you'll see they do some controls, right? And they look at the fluorescence decay, at the ellipticity, and one other metric during heat denaturation, or heat renaturation, I guess, guanidine denaturation, and one other way. Let's see here, kinetics, protein, better than that. Let's see. That's tryptophan specific. Tryptophan. It's a methionine. Sorry, it's a tryptophan methionine. It's not serine. It's methionine. But so here are some. I mean, I can't really answer your question. I don't think that there is a good answer to that question. And a lot of the flakiness of this paper comes from their interpretation of this diagram. And I'm sure that they only did this once. I'm sure that this was a source of terror among the graduate students, because they knew deep in their hearts that the entire paper rested on the interpretation of this couple diagrams here, right? And nobody was really completely confident with this. And when they first took these data, they were like, holy fuck, how are we ever going to interpret this? Right? And they took it into Mr. Sunshine, Dr. Sunshine, Grubely, right? And he drew these lines. And right? And what these lines then did was give Martin Sunshine Grubely, a license to interpret ellipticity as a function of temperature, as folded fraction as a function of temperature. Right? So now, this set of data here, this was done in a single shot, CD after CD after CD. They started out doing a whole fuck ton of them here. Then they got bored and it was getting super late, and they realized they were going to be doing this for 17 hours. So they took them every 5 degrees after that. They realized they had gotten 5 degrees and it took them all day. So they started going up in larger intervals here, right? And then this break here was when they went to the vending machine and they got into an argument about something completely science unrelated. So they missed this point. Then they took 2 in succession. And then the third one, then they were getting bored. Then somebody fell asleep, but they got this point and they finished it off here, right? So this uneven set of, sort of sparse set of data here underpins their entire paper. Right? Then, after they got to this point, they cooled it the hell back down to 20 degrees, 21 degrees, right? And they took another CD spectrum. And there's two possibilities. Basically, this could have been anywhere, right? But it wound up here, right? It's a damn good thing because it allowed Martin Sunshine Grimley to draw a line between this point and this point, and then base the entire fucking goddamn paper on his interpretation of folded fraction as a function of ellipticity.
Yeah, there's only like 1 point from the middle kind of half folded sites part. The denatured has a bunch of points, the native site has a bunch, and there's only one on that line.
Right, exactly. So they had to heat it up until it heat denatured, right? And this denatured state is different from this denatured state. It has to be, because this is irreversible, right? Because if this were reversible, it would have come back down, but it did not, right? So this is a different state of denatured than this. But what the hell? Dr. Sunshine was able to gloss that over, not mention it, right? And so they're able to say that the folding fraction between -4 and 21, this changes in this way, right? And all these little fucking dots here are based on these lines, not on these experiments, you know? So anyway, it's a good question. And I don't think it's really satisfactorily answered. But on the other hand, it's kind of an impossible question, right? It's like, how do you collapse all of the 20 trillion states of folding of this protein onto a single dimension, which is given by the kinetics of the stupid tryptophan decay, right? So it's this tau collapse. Wait, no, that's not it. Sorry. No, it's not here. This is the higher level one. There's a better paper for that, I think. How can you make it all? Yeah. So then you can do these steady state lifetime measurements, right? These are lifetime measurements based on the protein held at constant temperature, right?
And for this figure, that little square there, that is their control, right? They only took 1 point.
This one here, you mean?
Yeah, that little square in each one. They only looked at it at 1 point.
Right, exactly. Yeah.
That's the,
so yeah, this is a sperm whale mutant. Yeah. So I mean, cutting them a tiny break for not doing too much with the mutant DNA because they didn't have that much of it, you know. But these are all by exponential fits. They had to do a lot of massaging, right? They had to bi-exponentially fit, use a scatter component, which I'm not even sure what that is. And they used phase fluorimetry. I'm not sure what that means. Oh yeah, I do know what that means. How they got it so fast, I don't know. They calibrated against paratriphenol. They must have had a way to put some terphenyl into the cell. Terphenyl has probably a single exponential decay, et cetera, all that good stuff, and a known decay times, a known decay properties. So so all this change here, right? This is the triangles up here are in the open triangles are without guanidine. The open circles are with guanidine. And then these are all lifetimes, right? So there's 2 lifetimes that they fit to, like a 7-odd nanosecond and then a 2-odd nanosecond, right? And the long lifetime is more structurally sensitive than the short lifetime, because the short lifetime has no guanidine dependence, but the long lifetime does. And this is the lifetime. This is the amplitude. The lifetime and the amplitude of those 2 different components. And then, yeah, the sperm whale mutant was measured once at 20 degrees. And the sperm whale mutant did not have the methionine. So it will have sort of the, I don't know exactly how that works in there, but I guess it's at one of the extremes in terms of the modeling that they're going to do. So anyhow, I'm tired. Are you guys tired of this bullshit? God damn. Stupid kinetics. My God, will it ever end? So, Kai, how are you doing, sir?
Okay, I guess.
Did you understand any of this bullcrap?
I understood some of it, not the last part.
Okay, yeah, the last part is like, it's interpretive of the lifetimes. You know, like you can, like you keep blasting it, keep getting lifetimes, and then you interpret the lifetimes to mean it's folded or denatured, right? But how can you do that, right? That's the question that I think Adam or Richard or somebody had, or maybe Dan. No, it was Dan. It was like saying, how can you do that, really? Because there's so many different states available. You know, it could be folded this way or that way. It could be reaching around the back. Blah, 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 blah. And they're all just saying, well, it's basically this initial collapse, the cold denaturation just changes the distance between a tryptophan and a methionine. And that alters the lifetime of the tryptophan. Right? But it's absolutely relevant and absolutely true that that is not the only way to modulate that tryptophan lifetime. Absolutely not. There's a bazillion different ways. Oxygen, bazillion different things could be affecting that lifetime. And so, you know, I don't know. I mean, at a certain point you say, holy shit, I never could have done this. Let's just give him credit, right? But I still don't know if it's really science yet. Okay? Does anybody want to say anything? Calvin? Oh, no, that's just Calvin's chair, I think. Calvin of the empty chair. Lily?
No.
We're good? We're good? Ivy, we're good?
Barely hanging on by a thread.
Hanging on by a thread? Okay.
Biochemistry is not my forte.
Okay. Well, this is biophysics, right, Carla?
Yeah.
It's sort of biophysics, right? So,
Yeah.
That's not a really good hiding place just yet. But Pauline, how are we doing? Pauline,
I'm okay.
you're okay? You're following so far?
Kinda.
Yeah? How kinda and how not kinda?
Like I need to read through this again.
Okay. Alrighty. Okay. Bye, everybody. See you Tuesday. I promise I'll publish these questions.
Dr. Terrell,
Yes.
I have a totally unrelated question for you, but it has to do
Uh-huh.
with so basically at work I'm trying to detect B12 by fluorescence because I found some obscure paper that says they can do it, and it's not working at all, and I think they're live.
Yeah. Well, fluorescence is idiosyncratic, right? Fluorescence can be quenched and absorbed, and the excitation beam can be absorbed. And so there are lots of weirdness, especially if you're looking for the native fluorescence of a molecule like B12. So if there's any, there's other chromophoric sort of biomolecules, and there's other vitamins, right? I think it's niacin and no, there's niacin and another one of the B vitamins are very good light absorbers, and they have triplets, and so they could be wreaking havoc with this B12 one.
Well, no,
Also,
this is just a standard.
Uh-huh. Are you using a fluorescence detector in your HPLC?
Mm-hmm.
So, and you keep running up the standard and you get no signal, no signal, no signal?
I tried.
And have you tried a standard fluorophore like rhodamine or something like that?
I had melatonin and that fluoresced.
Okay. Well, it could be also that the B12 intensity is super low.
Yeah, I turned up the gain. I did all kinds of stuff.
What buffer are you using?
What is it? It's just formic acid, acetonitrile, and
formic acid.
Yeah.
There's your problem.
Really?
That son of a bitch is absorbing, and it's probably interacting with the triplet state. Because formic acid, which is lovely for HPLC MS, is also very gnarly in terms of chemical interactions. So, yeah.
Report back.
Yes. Try it with a sulfonic acid. I mean, you may not get any signal if you're going to do MS, but that'll give you a way to rule out the formate. Formate, that's a nasty little guy. Okay.
Thank you.
Excellent. All righty. Well, don't thank me yet. I probably sent you on a wild goose chase. Bye.